Okay, so I just wanted to recap here on how UTF-8 works. So we just need to see how that works. So like we saw before, for the code points from 0 to 127, the first bit of the byte is going to be 0. And when we see that that first bit is 0, we know this is a plain vanilla bog standard ASCII 1 byte character. So that's the easy one. However, if the first bit is not 0, then that's telling us that we've got a multi-byte character. So where we have 110, that's telling us that this is the first byte of a 2 byte character. Okay? And the 110 marks the start of the leading byte, and then the second byte, the continuation byte, is marked with a 10. So we saw this in the last class. And the important point here is that the payload is marked here across these bits. So although we're using 2 bytes and we're using 16 bits, we're only using 11 of those bits for data. So the 110 that marks the beginning of the leading byte and the 1 and the 0 that marks the beginning of the continuation byte, they're completely ignored, and we get the information we need from the remaining bytes. This can be extended then across multiple bytes. So where we have 3 bytes, the leading byte starts with 1110. You see there that the 3 ones means this character is spread across 3 bytes. And so to get the code point for this character, we need to go across 1, 2, 3 bytes. So here, the code point is B612, which in decimal is 46,000 and whatever. The 1110 here marks the beginning of the leading byte. So we know now that there are 2 more bytes coming. The 10 here are used to mark the beginning of the continuation byte, and the 1 and 0 here are marked to use the beginning of this continuation byte. So the payload here can be found in the last 4 bits of the first byte, and then the last 6 bits of the 2 continuation bytes. You'll notice that this will give us actually a total of 6 plus 6 plus 4, 16 bits altogether, which is exactly what we would need for a 2 byte code point. This can be extended then to 4 bytes. The 3 ones here tells us that there's 3 bytes in total. Okay, so the 3 ones followed by the 0 in the leading byte tells us that there's going to be 3. We can extend that to 4. And so here we've got 1, 2, 3, 4 ones and a 0 at the start of the leading byte. And then we have a 1, 0, 1, 0, and 1, 0 to mark the beginnings of the continuation bytes. Now this could be extended to 5 bytes and even to 6 bytes. And you could keep going. But as it turns out, it has been decided, that it was eventually decided that UTF would only go as far as 4 bytes. So you can have 1, 2, 3, 4 ones there, followed by a 0, telling you this is the beginning of a 4 byte sequence. Now here's the interesting question. And here we have a 4-byte sequence, right? So we're using 5 bits of this byte are used to mark the beginning of the sequence. That's the leading byte. And that makes sense. We do need to mark that in some way. But because we have the 4 ones here, we know this is a 4-byte sequence. Once we've seen that we've got 1, 1, 1, 1, we know to expect 3 more bytes. So the question is, do we really need to mark the continuation bytes? Do we really need to waste 2 of every 8 bytes when we know there were 3 more bytes coming anyway? And so in some respects, UTF-8 is a little bit inefficient. In fact, it's precisely this kind of inefficiency that caused us to use 3 bytes for every Japanese character when we could have only used 2. We know that we can, the code points for Japanese are in the range that can be coded in 2 bytes. We only need 16 bits to code Japanese. And yet in UTF-8 we end up using 3 when in fact 2 would have done. So on the face of it, that seems a bit wasteful. And in our UTF-8 sequence, in our UTF-8 text file in the lab yesterday, we noticed that from the numbers we figured out that the Japanese was taking 3 bytes, whereas when we saved it in UTF-16, the same code was saved with only 2 bytes. So just to be clear now, the issue though is the bits being wasted in the continuation bytes. We have to use the bits in the leading byte to tell us that this is special and this is how much is coming. But certainly we could have devised a system where we wouldn't waste these bits in the continuation bytes. But there's good reason for this. If, for example, this was a transmission from A to B and some bits were lost, the system would be very susceptible to errors. Also, we know that if you jump into this in the middle of the bytes somewhere, you'll know where you are more easily. So having the continuation bits marked makes it much easier to recover from errors or to know where you are if you just hop into the stream. So it is slightly more inefficient, but it's more robust, and so that's why we do it. So the exercise we have then is to decode this UTF-8 sequence. And the easiest way to do this is maybe to convert each of these hexadecimal digits to binary so that you can unpack the payload and then recode it to see what you should get.